Hi guys, welcome to GeeksforGeeks. In this video, we will talk about binomial coefficients. So first of all, let us understand what do we mean by a binomial coefficient. So given a binomial expression 1 plus x raised to n, we define Cn comma k, the binomial coefficient, as the coefficient of x raised to k in the expansion of 1 plus x raised to n. So for example, if we have 1 plus x square over here, we can write this in the expanded form as 1 plus 2x plus x square, and as you can see, the coefficient of x raised to 0 here is 1, and the coefficient of x raised to 1 is 2, and that of x raised to 2 is again 1, and that same thing is written over here as well. So this is one definition. Let us look at another definition of Cn comma k. So Cn comma k also gives us the number of ways in which we can choose k objects out of n objects. So if you remember from combinatorics, we have this formula n c k equals n factorial upon k factorial into n minus k factorial, and this also gives us the number of ways in which we can choose k objects out of n objects. So let us say I want to calculate c2 comma 0 using this formula. So I'll rewrite it as 2c0, and I'll put in the values of n and k. I get 2 factorial upon 0 factorial into 2 factorial, and this becomes 1, and that is what we saw earlier as well. So now that we know these two definitions, we can move on to our problem statement. So our problem statement is very simple. It says given n and k, calculate c n comma k. So for example, if we have n is equal to 4, k is equal to 2, we should return 6, and so on. So we just saw two ways to calculate Cn comma k. Now here is another standard formula. This also comes from combinatorics. So we have this recursive formula. What it does is it splits Cn comma k into two parts: Cn minus 1 comma k minus 1 plus Cn minus 1 comma k. So in order to calculate, we split it into two parts, and we keep on splitting until we reach one of these base conditions. So let's work it out for n is equal to 4 and k is equal to 2. So we have to calculate c4 comma 2. We split it into two parts, and we keep on doing until we reach the base conditions. And once we reach at the base conditions, we start substituting the values. So we add these two values to get 2 over here, and then we add these two values to get 3 over here. Similarly, we add these two values to get 2, and we add these two to get 3, and finally we add these two values to get 6, which is the answer. So let's see how to do this in C language. We have our method binomial coefficient that is receiving these two parameters, and the base cases are what we just saw earlier. If k is equal to 0 or n, we return 1. If not, we simply split the problem into the two subproblems and we return the sum. So if you noticed, we actually recalculated c2 comma 1 twice when calculating c4 comma 2. So this problem has the overlapping subproblems property as well, because we are recomputing we are trying to solve the same problem multiple times. In fact, let us look at this another example. For n is equal to 5 and k is equal to 2, we have the recursive tree drawn over here, and as you can see, this whole subtree c3 comma 1 is repeated over here. And furthermore, inside this subtree, we have this part c2 comma 1, which is repeated over here as well as over here. So we see that we are solving the same problems again and again, and as the values of n and k increase, the size of this recursive tree will also increase, and the number of computations that we are redoing will also increase. So we saw that this problem has the overlapping subproblem property, and it also has the optimal substructure property that we saw earlier. So this classifies as a dynamic programming problem, and we know that when approaching dynamic programming problems, we can instead of recomputing the same values again and again, instead of solving the same problems again and again, we can store the previously computed values in an array, and use them whenever those are needed in the future. So let's see how this is done using C language. So we again have the same method over here with the two parameters. So we begin with creating a two-dimensional table in which we will put in the values, and we run two loops. The first loop runs from I is equal to 0 to n, and the second loop runs from j is equal to 0 to min of I comma k. We'll get to this in a minute. So inside this loop again we see that we are using the same formula, except this time we are not making recursive calls. So what happens here is, again we are looking for the base cases. If j is equal to 0 or I, we put in Cij is equal to 1. However, if it isn't, instead of recursively calling the same function again, we are actually looking up in the table and using the values that were previously computed. So this is how we construct the table ci comma j, and finally once our loops exit, we return the value of c n comma k. Now why do we have this min I comma k over here? So if you remember, if you noticed, when we were calculating c4 comma 2, so we divided this into two problems, that was c3 comma 1 and 3 comma 2. However, in the expansion of 1 plus x raised to 3, we know that there are other terms as well, such as c3 comma 3. However, in this computation where k is only 2, we will never need c3 comma 3 or any such computation where let's say for different values of n, we won't need to calculate any value of nck where k is actually greater than 2. So this is why we have that condition in our loop over here, min I comma k. And so let's look at how this code works for the same example as we saw earlier. So for n is equal to 4 and k is equal to 2, let us look at the dry run happening over here. So for I is equal to 0, we calculate this value, and for I is equal to 1, we calculate these values. Now all these values satisfy the base condition, so we simply put in 1 whenever we wanted to calculate these values. And for I is equal to 2, we calculated these values. Now we see over here, when we were calculating c2 comma 1, we needed to have the values of c1 comma 0 and 1 comma 1, and we had already computed these values, so this time we did not solve these problems again. Instead we just did a lookup, and that same thing is again repeated over here. Instead of solving the same problems again, we simply did a lookup, and again over here, and finally we arrive at our answer. So in this manner, like when we use the DB approach, our time complexity becomes big O of n into k, and our auxiliary space complexity becomes big O of n raised to k. So that will be all for today. Thank you for watching. Please leave us your comments.